Hi, everybody. Welcome to the Hacking Dask, Diving into Dask Internals, a workshop put on by Julia Signell and James Bourbeau. Julia is head of open source at Saturn Cloud, and James is lead software engineer for open source at Coiled. Outside of that, welcome to the workshop, and I'm going to hand it over to them.
All right, thanks, Nathan. So for people who haven't got the tutorial materials yet, they're all available at this GitHub repo, which we'll throw in the chat again, I guess. And as we go, you can also put any questions that you might have in the Zoom chat, and we'll monitor that and try to respond to them as they come up and raise them if they seem like broadly relevant. There's two ways to run this tutorial. You can run it locally on your laptop, or you can use Binder, which is just a button from the GitHub page. So as Nathan said, I'm Julia Signell. I'm the head of open source at Saturn Cloud, which is an end-to-end data science platform that focuses on Dask to enable parallelized computing. And James, do you want to introduce yourself?
Yeah, sure. Like Nathan said, I am the lead open source engineer at Coiled, and we focus on scaling Python with Dask and making Dask work efficiently for teams.
Cool. So the goals of this tutorial are to cover the more advanced features of Dask. So we're going to talk a lot about weird things you can do with collections, task graph optimization, all the nitty-gritty about workers and schedulers and the plugin system, how to inspect state. So hopefully you'll walk away at least probably overwhelmed, but exposed to some of the more advanced stuff. And there's a little brief overview notebook in this version of the tutorial, but we really do assume that people are coming in with a prior knowledge of Dask. So if you're new to Dask, you should really go check out this the standard Dask tutorial, which is available at tutorial.dask.org. So throughout the tutorial, you'll see little prompts like this, where it'll ask for you to input solutions to exercises in Jupyter, in the Jupyter cell, and then there'll be a collapsed cell underneath that will have a solution. So that pattern will occur a couple times. And other than that, we'll just dive right in. So I'll pass it over to James.
Yeah, thanks, Julia. Let me go ahead and share my screen. Make sure I share the right one. Great. So you should see the repo. Yeah, so I posted a link to the repo and to the Binder setup as well in the Zoom chat. So let me pull up the next notebook. So we just went through 0 welcome. We're now going to go through the #1 overview notebook. So let me blow this text up a little bit. How's this looking? Big enough for folks?
I would even go bigger.
All right, we have now gone bigger. How's that looking? Okay, great, cool. Great, so yeah, as Julia said, we are assuming some prior Dask knowledge, even though we have this overview here. This overview, we're gonna get through this in about 10 minutes. It's just basically provide a foundation for the rest of the tutorial, talk about Dask at a high level, go through some of the APIs, but we are gonna go through them relatively quickly just so we can start diving in a little deeper into other topics. So with that said, Dask is a flexible open source library for parallel and distributed computing in Python. And I think I'm getting some sound from someone else. So if you could mute, please, that'd be very appreciated. So yeah, Dask is designed to scale the existing ecosystem, and there are several reasons why you might want to actually use Dask. The first is it enables parallel and larger than memory computations. So you can do a NumPy-like workload on a terabyte of data that you wouldn't necessarily be able to fit into your local machine, like on my laptop, for instance. And also, speaking of NumPy, uses familiar APIs that you are hopefully already used to using. So it implements the NumPy API, the Pandas API, the scikit-learn API. So you get to, the user experience is very similar, hopefully, to what you already have when you're running on smaller data sets on your local machine. So because we use the same APIs, it allows you to scale your existing code with really small, minimal code changes. Dask also works equally well both on your laptop and whenever you scale out to a cluster. So you don't have to, you can prototype using Dask on your laptop, and then when you need more computational power, you can then use a distributed cluster on, well, anywhere that you may have access to, and you don't have to change your tool set. You can use Dask in both these types of environments. And last thing I'll mention is Dask has built great built-in diagnostic tools. So we'll see these actually later on in this notebook. But yeah, this is also another great feature that Dask has that I in particular really like. So from a very high level, let's talk about the components of Dask. You can think of Dask really as consisting of two main components. The first is what we call collections or Dask collections. These are user interfaces like Dask Array and Dask DataFrame, Dask Delayed, the concurrent futures interface. All of these interfaces produce task graphs for you. So they don't actually perform computations. They more set up this task graph, which is kind of a recipe for the computation you would like to compute. So that's the first component, collections. The second component are schedulers. These are what take as input the task graph that your collections have set up and actually compute them. That's where the actual computation happens, potentially in parallel. And there are a few schedulers that we will talk about. So that's like the 10,000 foot high level overview of what makes up Dask. Let's now start talking a little bit about some of these components, the collections, task graphs, and schedulers. First, I want to kind of focus on the task graph part. So here I have some Python code. I have an increment function. I have an add function that do exactly what you think they do. And then we have some data here. We have a variable a and b, which are 1 and 12 respectively. We can then use these functions we've defined. We can use our increment functions, and then we can take the output from those increment functions and pass them into our add function and get some final output. There's like no Dask code here at all. This is just sort of vanilla Python code. And we can see we can print out the output, and it is 15. So we can take this code here, this sort of computation that we want to run, and we can convert that into a task graph representation, which is shown down here. So here, this is basically a graph of interrelated tasks. So where the circular or the circles here represent function calls. So here's an increment function call. Here's another increment function call. Here's an add function call. And these squares or rectangles here represent the output of functions. So we call our increment function and get some output. We call the increment function again and get a different output. And then we take those two, pass them into the add function. And that produces our final output here. So hopefully you can see the mapping between the code we have outlined up here, the computation we actually want to run, and the task graph down here that sort of represents this computation. You can see we're encoding all the dependencies here with these arrow structures. So that's sort of a simple example of a task graph, and we'll see some more complex examples as well. That's sort of the fundamental basics there. So now we've talked a little bit about task graphs. Let's zoom in on just a couple of these Dask collections that generate task graphs. We won't go through them all here. The first one I want to look at is Dask Array, and then next we'll look at Dask Delayed. So Dask arrays are chunked n-dimensional arrays. You can think of a Dask array as being composed of a bunch of NumPy arrays. I'll have a quick caveat here that Dask array actually works with lots of different array types. So the sort of canonical example is a NumPy array, but we also support sparse arrays, or if you're using GPUs, CuPy arrays as well. So, but just for now, we'll just in our head think of them as a collection of NumPy arrays. And Dask implements a large subset of the NumPy API using block algorithms. So the giant Dask array here is composed of a bunch of little squares here. Each of these squares is a NumPy array, and the algorithms that Dask array internally uses basically work with the individual chunks here. They work with, they'll load a few chunks in at a time, generate some task graph that we then represents, or that then results in the actual computation that you want to perform happening. And we'll see an example of a task graph generated by Dask arrays momentarily. And for many purposes, Dask arrays can serve as basically a drop-in replacement for NumPy that gives you scalability. So let's look at some examples. So we can import NumPy as NP. That's sort of the canonical way to do that. And the corresponding import for Dask is import dask.array as DA. So hopefully we all are familiar with NumPy, and we can, for instance, generate a two-dimensional random array where each dimension has length 1,000, sort of using NumPy random.random. We can do a similar thing with Dask but the only difference is we have to, so notice the import structure looks exactly the same, except DA instead of NP. We have to specify the chunk size here. So when we're taking our Dask array and breaking it up into chunks, how big do we want those chunks to be? So here I'm just arbitrarily choosing my chunks to be 250 by in this case, I guess 500. And there is, here is our array here. So Dask arrays have nice HTML wrappers if you're working in JupyterLab. So you can see we have information about the entire array as well as the individual chunks that comprise the array. And here we can kind of see, if your chunks are small enough, or rather, if you have a small enough number of chunks, you can kind of actually see the chunk structure here. So Dask arrays, much like NumPy arrays, have all the sort of normal attributes you would expect. They have D types, they have a shape attribute, etc. They really do look and feel like NumPy arrays. However, they are lazily evaluated. So up here, when I created this Dask array, I didn't actually do any computation really. I just set up the task graph that later on I can compute if I want to. To visualize a task graph for any Dask collection, Dask arrays included, you can call their visualize method, which I'll do here. So here you can see, remember we're calling Dask's random.random. What that actually ends up under the hood doing is setting up a computation where we call NumPy's random function a bunch of times, once for each chunk. So we can see here, we're going to call NumPy's random sample, and we will, this generates the 0, 0 chunk. So first chunk in the 0 dimension, first chunk in the 1 dimension. Same thing for, you kind of work your way across the chunks up here in the wrapper. So for each of these chunks, we will have a NumPy random call. And if we want to actually compute this array or any Dask collection, you can then go ahead and call compute. And at that, we'll circle back to that in a little bit. For now, we're just going to ignore some subtleties there, but you call compute and the task graph is executed. So here we can see we called compute, we stored that in some result, and we actually get back a concrete NumPy array. It's not this abstract task graph thing. It's just a good old-fashioned NumPy array. So this was a relatively straightforward example. We just called random. However, Dask has implemented a large subset of the NumPy API. So things like arithmetic, reductions, tensor contractions, things like tensor dot, access reordering, things like transpose, slicing, fancy indexing, a lot of the array protocols like array ufunc, array function, things like that. I'm not going to go into all the detail of all the things that are supported, and I'll instead point you to the Dask array API docs, which you'll see here. There's, first off, there's many functions, and they all look hopefully very similar to the NumPy experience. So things like flip and histogram, and I saw Doug is on the call. So, there's histogram DD, which he recently implemented. Thank you, Doug. So yeah, there's that. So we can use this API we have access to build up more complex computations. So for instance, I could take my 2D Dask array X, I can do NumPy things, like I can add it to its transpose, I can take a sum across an axis and a mean, and get build up some more complicated task graph that looks like this. So we can see all the circles here are different functions that are getting called, and the squares are the outputs that are getting piped in generally to other function calls. So we can see here's all the random samples down here for generating our arrays, and then each of those chunks go off into other things. Like we can see there's like a transpose function getting called here. There's an add function getting called here. We're doing some tree aggregation here where we're calling the mean. So you can kind of see how how this relates to the actual computation we want to do, transpose, summing, meaning. But we didn't actually have to build this task graph for ourselves. Dask implements this for us. We can just use the NumPy API that we like, and Dask takes care of everything else for us. I can then compute this also, like just call compute. There's the result. It'll go through that task graph and compute everything. So that's it for Dask Array. And that's sort of a high level, we refer to that as a high level or a high level API. It's a high level collection. So that'd be things like Dask DataFrame and Dask Array. This is where you're not actually constructing the task graph yourself manually. You're kind of like using the NumPy API and Dask is constructing the task graph for you. That's really useful, but not, there are some situations that don't fit nicely into like a DataFrame or API scenario. So for those, we offer Dask offers other interfaces for lower level interfaces for constructing task graphs manually. This is great if you have some custom code laying around that you'd like to parallelize. So for instance, one such example would be, I have 3 Python functions here, inc, double, and add. And I've added some sleeps here just to kind of simulate some actual work being done. And we can define those. And then we have some code down here that uses those functions. So we have some data here that we loop over. We increment some of the data, we double it, then we take those 2 things and add them together. And then at the end, we end up taking a sum of all of the outputs here. We can see that took about 6 seconds, so 5.85 seconds to do. However, you'll notice that inside this for loop, and as we're going through each loop in the for loop, each loop itself is independent. So they don't depend on other iterations through this for loop. So this sort of lends itself nicely to parallelism. We can run different parts of this for loop in parallel. To do that with Dask, what we'll do is from Dask, we'll import the delayed decorator. And this is the API for the Dask delayed interface as this decorator. So we can take a function here. So here, this function actually looks exactly the same as the increment function before. I'm just calling it lazy so we can keep both versions around. And I'm adding the delayed decorator. So what that does is that actually creates this delayed object. So this will behave almost exactly like our the normal Python function that is undecorated here, except it will actually, any inputs you give it, it will actually cache those and kind of construct the task graph itself under the hood and produce a delayed object. So that's just another Dask collection, kind of like a Dask array that you can call visualize on and you can call compute on later. So it's lazily evaluated, but it sort of lets you say, I want to run this task and then this task explicitly. So we can like take this lazy inc function, pass in 3, for instance, and get some output. It didn't return 4, it returned this delayed object because it's building up a task graph internally for us. We can call compute on it and get the result. We can get 4 out of this by calling compute. We can also take delayed objects and pass them to other delayed objects. We can also pass undelayed, like 3, for instance, objects to delayed functions to build up this task graph manually. So this was just calling our delayed function once on 3. I can now take that output and pass it to the delayed function again. And so that's kind of like calling the delayed function twice sequentially. We can see it internally that built up a task graph for me. It said, call the lazy increment function, get your output, pass that back to the lazy increment function again to get the actual final output. And this is all just using normal Python function composition. And now we have 5 because we've incremented 3 twice. So circling back to our original example, we have our 3 functions here, inc, double, and add. I've just now added delayed decorators to them. And I've also added delayed to my sum that we're calling down here. And that's it. All the other code looks exactly the same as the non-parallel version. Notice that happened really quickly because it just set up the task graph. It didn't actually do a computation. We look at that task graph. Here we can see these, like each of these branches here is one loop, one iteration of the for loop. We're inking, we're doubling, we're adding, we're summing at the end to get our final result, which at the end of the day is 34 whenever we actually go ahead and compute this. So, and notice that took a second, or that took 2 seconds instead of 6 seconds, like the synchronous example took. So that's it for the Dask collections. So we have these high-level collections for generating task graphs sort of automatically for us underneath the hood. And we also have a lower level interfaces like Dask delayed for sort of manually constructing the task graph you want for some custom logic. Let's now talk about schedulers. And I realize we're running a little low on time, so I will make sure to go through this a little faster this section. So schedulers are what actually takes the task graph and compute them. So here's a nice little animation of a scheduler going through some task graph and actually computing things as it goes. There are two flavors of schedulers. There are single machine schedulers. These only work on a single box, a single machine, and they require no setup. So there is the multi-threaded scheduler, multi-processing scheduler, and the single-threaded scheduler that will take tasks in a task graph and submit them to the multi-threaded scheduler will submit them to a concurrent futures thread pool executor. The multi-processing scheduler uses a process pool executor, and the single-threaded scheduler just runs in the main thread. There's no parallelism there for the single-threaded scheduler. That's mostly used for debugging. And all of the Dask collections have their own default scheduler that they will use automatically if you don't tell it to use something else. For instance, Dask array and Dask delayed, the things we just walked through, both use the multi-threaded scheduler by default. So there are several ways you can set the scheduler. So you can set it globally using dask.config.set scheduler equals. Any calls to compute after this will use the multi-threaded scheduler. You can also use it as a context manager to set the default scheduler within a certain context. You can also go a little more fine grain, and in an individual compute call, you can say scheduler equal threads or scheduler equals processes. So for the threads and processes schedulers, you can also pass in a num workers keyword argument, and that just will specify the size of the executor, the size of the thread pool executor, the size of the process pool executor. And then, so that's like the first flavor of schedulers, the single machine ones. The other flavor, and this is what we'll talk about in more detail later in the tutorial, is the distributed scheduler. We'll actually kind of maybe go through all of this later, so I won't say anything here other than the distributed scheduler is like the advanced scheduler. It works on a single machine, but it also works in distributed environments across many machines, and has lots of great features, which we won't go into here just due to time, but things like the concurrent futures like interface, sophisticated memory management. It takes into account data locality. It tries to move computation to where data already is, as opposed to moving data to where computation is. We have adaptive employments where you can spin up and spin down workers depending on demand in the cluster. And yeah, the last thing I want to highlight here is the, I mentioned before, the diagnostic tools. So I'm just going to really quick pull up the Dask dashboard here so we can see that in action. So here I've spun up a distributed cluster on my laptop just by instantiating this client object. I'll then do some Dask array computation and compute. And here we can see all these tasks flying by. We're seeing progress on all, as we're going through the task graph, the total progress for all the different tasks. We can see the number of tasks processing on each worker, bytes stored in each worker, etc. This is super useful, and we'll dive into this more a little later. So with that, I will turn it over to Julia. The sort of structure for the rest of the tutorial, there's kind of two acts. The first act, Julia will be going through kind of diving into more advanced patterns and collections. And so kind of going back up to this diagram up here, Julia will be sort of diving into advanced operations on like Dask collections and task graphs. And then for the second act, I'll be diving more into the distributed scheduler in particular. And with that, Julia, you want to take over? Okay, Julia.
Yeah. Okay. Focused on sharing the screen first. Yeah, thanks, James. And just for like a PSA, we will be taking breaks, so don't stress out. We'll give you break times at some point in this 3-hour tutorial. So no need to set those for yourself. Okay, so in the overview notebook, we talked about some of the predefined, some of the different Dask collections like arrays and delayed data. We didn't talk about data frames, but we'll talk about those a bit in here. Those collections all have operations like mean, max, all the standard like NumPy like, pandas like APIs. And those support standard operations that you'll expect. But in this notebook, we're going to talk about how those operations are implemented, and then we'll learn how to construct our own operations using Dask arrays and Dask data frames. So the goal is to both understand a bit more about the internals and to learn from the implementation about how you can create your own custom functions. So let's step back to the blocked algorithms that James was talking about how these types of things like Dask array random.random is implemented. So it's implemented by applying. So we'll look at this. This task graph that we talked about in the overview notebook, and you can see this really involved task graph. And so we can break it down a little bit, and we can talk about just the first part, just the setting up the X array, which is DA random.random, and the transpose. And we can look at how the first part is to just apply, just take each of these little pieces and compute the random on just that part. So these circles here, and then each of those chunks gets a transpose applied to it. So this is a fully blocked algorithm where each of the chunks is operating in isolation, and it's entirely parallelizable. Each of these can happen without any communication between them. So that's the kind of things that we're going to be looking at in this notebook. And in this perfectly parallelizable situation, you can it's easy to construct these graphs using the NumPy API. But Dask also exposes ways for you to not just use the NumPy API, but to create custom block by block computations using map blocks, map partitions, map overlap. So the reason why you might want to use these things is for custom IO operations, for executing, for applying embarrassingly parallel functions where there's no existing Dask implementation. And how they work is for each block, you're going to get the function applied just to that block, and the output will have a similar shape as, and the chunk will have the same location as the input. So there's kind of this direct mapping from the input to the output. So we can start by looking at map blocks, which is the Dask array custom mapping operation. And we can imagine that if there were no DA random.random, what would you do, right? You can create your own version using map blocks. So we can import NumPy, we can create this function, which just wraps NumPy random. And so for a particular size array, and then we can call da.mapblocks, give our function, and then we can declare how big the chunks are going to be. So there's going to be 8 chunks, and they're each going to have 250 on the first axis and 500 on the second axis. Then the other thing we need to specify is the D type. So this is an example of constructing an array. So using just the NumPy operation and map blocks. So let's see what that operation looks like. You'll see that it looks pretty much the same actually as DA random.random. So it's the same, basically the same operation. And if you call .compute, you'll see that you get what you expect. It has the right shape. It has the right kind of values. So in this, we pass the chunks argument. You'll see that we have to explicitly declare what the chunks will be like. That shows both the shape of each chunk and the number of total chunks. So 8 chunks, each with 250 by 500. There's also like a shorthand version of writing the chunks argument that you'll see popping up in different places, where you write it just the shape of one of the chunks. So 250, 500. It means the same thing. But it can be really helpful to specify the output chunks when you're using map blocks, because you can guarantee that the output will have the right shape, and it lets you properly chain together other operations. So operations that depend on the shape of the result of this will have the right values. You can always check what the shape and chunk information is by looking at this like pretty HTML display, or you can do it more manually by looking at x.chunks or x.something blocks. That's the pattern of the chunks, and chunks is the same thing that we inputted here. So it's the total shape of each chunk. So in that last example, we created an array from scratch using just D types and chunks and then our NumPy function. It's probably more common to use map blocks on existing arrays. So you can use it on one array by just calling array.mapblocks. You can also use it on several arrays. So here's an example where there's two different arrays, A and B. So the important thing is that they both have the same number of chunks. So they both have 10 chunks. And the shape of them, the shape of each of those chunks is actually different. And so the shape of the total array is different, but the number of chunks and the chunk pattern where the chunks are located is the same. So we can map them together. So how we do that is we can write a function that takes in two arrays. So this function, for instance, takes in A and B, it gets the max of each, and then it returns a NumPy array with those values in it. So we can call map blocks with our function, our two arrays, and then we'll specify that the output will have this chunk shape of 2. So see what that looks like. So you can see each of the little chunks from A and B going into the function and then coming out the other side. And we can also see that if we just look at this result, it has a shape of 1 by 20. So it's 10 chunks, each with shape 2. So there's special arguments that you can use with map blocks that are often convenient. These are block ID and block info. So we can take a look at what those, we'll just print them out. We'll just print out block info in that same function that we had above where we're taking the maxes. We can just print it out and see what it looks like. It's a little overwhelming, but the none is the shape of the output or all the information about the output. So it tells you the chunk location. It tells you the chunk location of the output for this particular run through the function. In this case, we're only printing it out once, right? So for this particular iteration to the function, it's the array location, the chunk location, the chunk shape, the D type, and then we also have that same information for each of the input arrays. So the array location will be the location along the regular data index, and the chunk location will be the index within the chunk shape. So within the num blocks, basically. And then you can see the output here. So one of the things that people use block info and block ID for is to create arrays from scratch by reading in specific files for each block. So that's what this example is here. There's a puzzle that is just a picture of a bicycle that's split up into 4 different little pieces. So there's an exercise where you can create your own reader function to read in just one file using the block ID to pick the correct file. And then you can pass that reader into map blocks with the chunk shape and the D type, and all the chunks will come together into the final result. So I'll give you some time to work on that. I'll give you 4 minutes. But if you have any questions, now is also a good time for that.
Hey, Julia, Doug had a good question in the chat. Since chunks are not necessarily conserved between the input and output of map blocks, does that imply that the shape of the input and output do not have to be identical?
So the chunks are conserved between input and output, but the shape of each chunk can change. So the shape of the overall array can change. but the pattern of the chunks will stay the same. So if you have it 2 by 2, 2 chunks by 2 chunks, then your output will be 2 chunks by 2 chunks. But the shape of each of those chunks can grow or shrink based on your function. We'll be looking at the rest of this notebook will deal with other mechanisms for applying custom operations that do things like flip the chunks or move them about in different ways. And then also ones that reduce the dimensionality, where the shape of where the actual chunks will be reduced.
There's another good question. Is the number of tasks always equal to the number of chunks?
I would say for this particular layer of the task graph, yes, I would expect that to be true, where there would be one task for each of the blocks. But you might be building, if you're not creating an array from scratch, then you might be building on top of an array that the array will already have a bunch of tasks in its task graph. So it'll get more complex.
Yeah, and also if you then do something with this array after you've already called map blocks, like take a sum or some other operation, cosine of it, then your overall graph will be larger. But yeah, so maybe to zoom in on your question, maybe reiterate exactly what Julia said, like the map blocks part, there is a one-to-one mapping between like the number of tasks and the number of chunks, but the number of tasks is just for the map blocks operation. The whole graph could be much larger.
Yeah.
Awesome. Okay.
All right. I think that's about the time I said. I said 4 minutes. All right, so let's look at the solution here. So you can take the block ID, take out the first and the second index from it, and then you can write the file path with those values in it and read in that file. So there's probably a bunch of other ways to do this, but this is one way that works. And you can see you get your image of the bicycle. Very satisfying. All right, so now we're going to move on to talking about map partitions. It's similar to map blocks, but for data frames. So it's got a lot of the same functionality. We'll go through it more quickly. But here's just a simple example of using this. We're going to use this little time series data set that is very convenient little helper function in Dask that just makes a time series of a bunch of people's names. And we're going to map the partitions to find where the column X plus column Y is greater than 0. So this is just a little toy example. And we can see that we get an output that's just a series of Booleans. Internally, map partitions is used to implement a lot of the helper methods in Dask DataFrame that make it look like pandas. So for instance, this is what it looks like to have the index. This is what the index for Dask.DataFrame is, how it's implemented. So it's just a map partitions with a get adder that takes in the word index. And then there's some extra keyword arguments, but essentially it's just a map partitions. So for each little chunk, it's doing this get adder. So you'll see there's a meta that gets passed in here. So it's kind of important to understand the meta argument in Dask. So all Dask data frames and Dask arrays has a special attribute called _meta that lets them know the metadata about the type of data frame array that they represent. So this metadata lets Dask know the D type of the object, the column names in order for Dask data frames, the name of the object, and the type. So whether it's a pandas data frame, a cuDF data frame, a NumPy array, a CUDA array. You can always look at this meta by doing by printing out underscore meta. This might not be obvious, but this is a pandas data frame, which has the column names, and then it's an empty one, so it has the column names, and it also stores the D type of all of these different columns. So that's how Dask knows what to render when you display a Dask object, because it doesn't have access to the data, right? It hasn't computed it yet, but it does know about the metadata from this underscore meta attribute. So that's how it has all this information here. So there's a couple benefits to this approach. When you add an item to the task graph, Dask runs the function on that little tiny meta, and that lets Dask know what the shape of the output will be, and it also allows Dask to fail fast if there's issues with like D types and like the type of thing you're trying to do. So here's an example of df.sum. So you can see that from this data frame that we started with, Dask knows that by using this meta, Dask can know that when you compute sum, you're going to be getting a series where instead of the columns, you're going to have an index of all those column names. And you can also Dask can also know that like this will work, like the ddf.name.string that starts with, that's an available method because the D type of name is a object probably or a string. So you can try using starts with a different column, and well, you get an error because Dask tries to run on that meta, and you can't run string methods on non-string columns. So when you sometimes the meta can't be computed by default, or the wrong value is, or it doesn't come up with the right result. So you can also oftentimes specify the meta in the function call. So in map partitions, you can say, this is the same map partitions we had above, and you can just say, oh yeah, and the meta of the output is going to be Boolean. So that is shorthand for saying the meta of the output is going to be a pandas series of D-type Boolean. That's often helpful. Dask will try to tell you when there's issues and it doesn't know how to get the meta properly. But that's often a helpful thing you can do when you're running more complex operations using map blocks, map partitions, and things. So now we're going to talk. So far, we've been talking about entirely parallelizable computations. So computations that only depend on one block to get the results that you want. Sometimes you need a little information from neighboring blocks. So some examples of that are rolling means, doing like convolving a filter across an image, and like anything where you need information, not just about this individual block, but also something about the next block. So you can think of it as like sharing a little data between neighbors. So this is a little more expensive, but so in Dask, the data will be transferred to, a little bit of data will be shared. So some data will be in multiple different tasks, some tasks will depend on a little bit more than one block, but it allows you to do these computations that you wouldn't otherwise be able to do. So here's an example where we're calculating the derivative. So here's this little graph, and we can use map blocks or map overlap by setting the depth as 1. So share, this means like basically share one value on either side of my array. And we can calculate the derivative by just rolling 1 and subtracting. So you can see the slope here. So we can look at the task graph for this. It's a little giant in this view, but the most important part is that it's mostly 2 separate towers of operation. one for each block. But then there's a little bit of overlap there in the middle. So that can be really helpful. And it's map overlap is used to implement all these different like rolling and things. So here's another exercise. It is to apply this example from SciPy docs and to make it blockwise, essentially, and to make it a blocked example. So here's a little array. This is actually an image. And then you can apply this Gaussian filter to sort of like smooth it out. So I'm going to give you a break here and you can work on this, ask me questions, but we'll reconvene in 10 minutes. So we'll reconvene at, in my time, 10:56. All right, so I'll be here, but I'll leave you to work on this or take a break. All right, so hopefully everyone's back. So we have some questions in the chat about this example, this exercise. So yeah, so you can really set the depth and the boundary. A lot of values will look reasonable, but here's what I came up with. So basically the sigma and the depth probably need to work in a way that makes sense. You can try changing the depth to a smaller value, and you'll see, for example, 0 is a nice value, and you can see the edges of the blocks showing up because they don't have the information from the neighbors to do this this Gaussian filter properly. So there's a question about, is it possible to apply the boundary condition only at the outer boundary? I am not sure. I think, oh, actually, I think that's the only place it does apply. Is only at the outer boundary, because at the others, it'll get the information from the neighbors. If that makes sense. Let me know if that doesn't make sense. And then there's a question about the chunks argument to map blocks. It seems like you can provide the wrong size and still get the right results. Yes, you can, but your meta will be wrong, right? So Dask won't understand what the shape of your output is going to be, or won't have the right values in there. So you can, when you call compute, it'll work, but since Dask doesn't understand the shape, you will not, when you chain together different operations, it won't work necessarily. So it's better to try and make the chunks match the chunks of your output accurate for what the output will actually be shaped like. For the depth, there's a question about depth equals an integer. Is that shared on both axes? The answer is yes. So it'll get the 0 axis and the 1 axis. It'll share both those neighbors. I think you can also pass a dictionary to depth to specify different values, or a tuple. Yeah. All right. James is also getting these. Okay. I think that's all the questions that came up. So let's move on to blockwise computations. So blockwise computations are probably one of the most powerful things we'll discuss in this notebook, and they are actually used internally to implement map blocks, and also to implement reduction and a lot of the other things, basically any element-wise methods on the array API. So they can do simple mappings, like adding to arrays. They can do operations that flip the data set, like transpose. They can do reductions like tensor dot, inner product. Those can all be implemented with this blockwise approach. So internally, here's an example. This is the code that's used for implementing transpose. So it takes in an array, it takes in these axes, and then essentially it just does a blockwise with numpy.transpose and flips the direction of the axes. So it both does the transpose on each individual block, and then it also transposes all of the blocks. So we'll re-implement transpose here. So if you're familiar with like matrix math, then these things are going to look very familiar. So here's a re-implementation of the transpose. So you pass its da.blockwise, and then you pass in the function that you want to apply to each block. The axis ordering of your output, the input array, and the axis ordering of your input. So here is it's the same thing we've been looking at, this random sample and the transpose, and you can see that for each of these chunks, we're going to do a transpose, and then we're mapping it. You'll notice that it's kind of hard to notice, but the little chunk location here that's being displayed, 0, 1, switches to being 1, 0. So we're both doing the transpose on the individual blocks and flipping all the blocks. You can also use blockwise to operate on multiple arrays. You just keep passing in more and more arguments. So here's numpy.add to add the x and x.transpose. So you can see what that looks like. It gets starting to get more complex. So this is equivalent to doing just x plus x dot t. It's the same thing. You could probably spend some time looking and trying to convince yourself of that, these two task graphs. So you can also increase or decrease the dimensionality of the output by changing the out index, that first ij or ji or whatever. So there's a lot more examples of using blockwise. So you can just look at the doc string if you want, or look directly at the docs that I've linked at the top of this section. Reduction so every Dask collection also has a reduction method. It's a generalized method that supports operations that reduce the dimensionality of the inputs. The difference between blockwise and reduction is that with reduction, you have finer grained control over the behavior of the tree reduce. So in blockwise, we have one function that we're applying to all the blocks, and then we apply it again. But in reduction, you can specify different functions for each of those. This will make more sense, I think, when I show it. But this is an example of our internal use of reduction to support the .sum method, where we are just doing a reduction on the array, and then we pass in the function that we want to apply to each chunk, and then we pass in the function that we want to use in the tree reduce. So here is that written out a little more simply. We implemented using just da.reduction. So it's our same little random sample. And then we do a sum on each of those chunks. And then we do this, we take every 4, that's just some heuristic that is every 4th. And then we sum them again into the partial sum. And then we bring it all together and aggregate it at the end. So this is the tree that I was talking about. And we have control over each of those steps, what the function is. So in this case, it's numpy.sum, and then you do numpy.sum again. But when you're doing other things like mean, then the reduction is not going to be the exact same at every step. So you can, one of the important things I want to talk about is you can see how the graph changes. The chunk size here determines the number of layers, the number of chunks rather determines the number of layers in this graph. So you can experiment with different chunk sizes. Like if you have 100 and 250, then your graph gets a lot bigger because you have a lot more chunks. But they're still doing this like tree reduce where they're stepping up and aggregating and re-aggregating until they get to the final product. So there's a split every argument that controls the number of chunk outputs that's included in each partial call. So you can control, I said that there's this heuristic, it's 4 of how many of these chunk results are going into each partial. But you can also specify that explicitly. So here is using split every to say every 5 blocks along the 0 axis, and every 2 blocks along the 1 axis. We're going to use that. So we're going to use 10 blocks in each partial sum. So you can see what that looks like. Every 10 blocks, and then there's a little, they go together into this this partial sum. So that can be a good thing to have in your back pocket when you're setting up custom operations that, or really when you're using, even when you're using regular the regular array API, you can use split every to control the shape of your graph. So you can try messing around with it. I'll probably just skip that for now. So another form of reduction is these group by aggregations. Pretty much, you know, if you want to do a group by, so it's kind of slightly separate. You don't really need to distinguish it as much from the other methods, but it's very similar to the reduction where you have different different functions that you call on each chunk. And then you have a function that you call on the concatenated output from several chunks, and then you have a function that you call at the end to return the result. So this is an example of calculating a custom mean on a group by object. So this is Dask DataFrame. In case I don't think I said that, but So it's a slightly different setup, but we're going to have that same data set of the time series. And for every chunk, we're going to calculate the count of the count of the values, and then we're going to sum. And then for the partial function, we're going to take those take the results of that of each chunk, and then we're going to do the sum of what those again, sum of each of those, sum of the count, sum of the sum, and then finally we'll divide the sum by the total count. So this is a breakdown again of how exactly that works. So you can see the output here where the index is now the name, and then we have the mean of each of these different columns. So this is equivalent to calling tdf.groupby.name.mean. So there is an implementation of mean.groupby, but you can implement any custom aggregation for group bys using this approach. You can look at the different graphs and compare them to convince yourself that they're similar. So there's also this apply method where you can apply random or arbitrary functions to group bys, but this is often not a good choice because when you do that, it'll shuffle all your data to put each group in its own partition. So custom aggregations are preferable because in them each partition is grouped, but it's not repartitioned, so it's a lot faster. You can run this if you want. It'll probably take some time. I think it took 50 times slower on my computer than the custom aggregation. Okay, so the last thing I'm going to talk about in this notebook is Dask delete. So you can write arbitrary functions in Dask delete and parallelize them. But if you're operating on a Dask collection or several Dask collections, Dask delete doesn't understand the organization of your blocks. So you can convert your collection into individual blocks, or you can operate, set up the computation and then arrange them again, or you can operate on the whole thing, just the whole array without applying the function block by block. So that sometimes works, but you can run into memory issues and it can be very slow. So we'll see what that looks like. So here's our array. So this is the standard way of setting it up where we have the da_random.random. We can do the same. We looked at doing that with map blocks, setting up this function. We can also set up this array using Dask array, where we have this random sample, which is just wraps numpy.random.random, pop in a delayed wrapper on it. And then we can take the results from this, use from delayed to produce an array from the delayed object, and then concatenate 4 of those, and then concatenate 2 of the whole thing. So you'll see that it has the shape that we want, where it has 4 along the 0 axis, 2 along the 1 axis, and this is equivalent to. This is how you would implement it using Dask delayed purely. So it's a little more involved if you're doing operations where the blocks have to be in particular spots. So Dask delayed is often not a great choice because it takes more to try and like write that kind of thing. So similarly, that was creating an array from scratch. Similarly, we can operate on an existing array using Dask delayed. So we'll write a Dask delayed version of transpose. And you can, let's visualize regular transpose, just to have that in our minds. And if you naively call the delayed version of transpose on X, you'll see that what happens first is all of the blocks come together into one, and then transpose gets called. So that's the risk of using delayed on Dask collections, is that they first get finalized and then they go. So all your data is in one place. So that can be okay if your data is small enough, or if and if it's relatively quick to compute this function on all of it. The like more proper way, if you want to keep applying your transpose block by block, is to first use this toDelayed method, which is available on every Dask collection, and convert it to an array of delayed objects. So here there's, for each block, there's a delayed object that represents that block. And they're in this nested list that represents the block structure, so the pattern of the blocks. So like we did it before, we can call our transpose function, and we can use this data from delayed to make an array out of this delayed object, and then we can concatenate, and then we can concatenate again. So we end up with our transposed array, and you can see this, that our graph is now parallelized rather than this like great coming together. We have these separate block operations. So there's a lot of different approaches outlined in this notebook. So it can be sort of confusing, like when to use which method. My goal is really to like show you all the different ways you can implement custom functionality for Dask collections. So different ones are useful in different situations. Map blocks, map partitions are good when your input block pattern matches your output block pattern, and the function is fully parallelizable. Map overlap is great for when you need information from your neighboring chunks. Blockwise is good for when you're, it's pretty good for a lot of things, but it's really useful for when you want your blocks to be in different orientations and your input versus your output. Reductions are good for shrinking and dimensionality, especially when you need different functions for different steps in your tree reduce. Group by, so you're doing group bys, and Dask delayed. If you don't have a complex block organization, but data is small, the computation is pretty fast, Dask delayed can be a good option. It's often the simplest to set up, but the slowest to compute on. So with that, I'm going to step away from custom operations and into graph optimizations. So in this notebook, we're going to, I guess I should maybe pause. Are there any questions, James?
Yeah, there's one question that was just asked by Timothy Smith. Is there an overhead involved with converting a collection to from delayed? This seems like a lot of trouble for similar same behavior.
Yes, there's some overhead in that, like it's a task that will be added to your graph. I'm not sure how it would compare to the compute time of like the actual functionality. I guess it depends on your task. So yes, it definitely adds complexity, and that will always add some overhead. So most of the time, if you can coerce it into one of the other patterns, the map blocks, blockwise, reduction, that'll often be better.
Yep, and what you get for that added complexity is you can do whatever you want. Like map blocks and map overlap have, while they are flexible, apply certain operations. So like sometimes you need to drop down to delayed because you want to do something crazy with the individual chunks. So like there is this overhead, but you get access to the individual chunks that you can play around with in whatever way you want. So that's kind of what you get for the small overhead that's introduced.
Yeah.
Good question though. Thanks,
Yeah.
Timothy.
All right. So switching gears, in this notebook, we're going to be talking less about collections and more about task graphs directly. So just to prepare yourselves. So the point of graph optimizations is to simplify computation and improve parallelism. So simplify computation by getting rid of steps that we don't actually need to get to our end result, improving parallelism by merging together tasks so that we can send, in shrinking the overall task graph, there's a lot of benefits to this. Like it makes it easier to serialize, it makes it easier to send the right tasks to the right workers. It doesn't burden the scheduler overly much with a bunch of small tasks. Graph optimizations are one of the really nice features of having a task graph at all. So we talk a lot about lazy evaluation and how Dask doesn't compute right away when you set up a function, but or an operation. But one of the benefits of having that task graph stored is that when you do call compute, we're able to optimize it to just get the part of the graph that's actually important for your result, and to just get the simplest version of that graph. So that's the goal of graph optimizations. So all of the collections that we've talked about, Dask Array, DataFrame, Delayed, they have graph optimizations already that are applied to them when you call compute. So normally you don't have to think about very much like what these graph optimizations are doing, but we're going to look at them a little bit, look at the common ones here. So those are cull, which is for removing unnecessary tasks, fuse, which is for fusing many tasks into one, and then inline and inline functions, which just replace keys with values that are easy to compute. So by using all those different tools, you get speed ups to your actual computation. So this is an example that's in the doc, so people might have seen it before, but it's a word counting example, and it's just a toy example which will help us understand cull, fuse, inline. So we're counting the frequency of the words orange, apple, and pear, and then we're starting with this list of words. So here we're constructing a task graph manually, like it's just a dictionary that we're making. So here are the words that we're going to start with, and then we're going to be counting the frequency of each of those words with this count method. We're going to be, and then we're going to do a formatting of the output using this function, and then we're going to print and return. So you can see this dependency graph building up, this task graph, and we'll visualize that here. I'm going to actually pop this out next to it so that we can keep track of this task graph as we go along and see how it changes. So we're starting with our inputs. Let me scroll to the dictionary so you can see. So orange, apple, and pear, and then all of our words. And then you can see that we have these count functions. We have the count of all the words, and then the formatting, and then the printing. So the first operation that we're going to look at is cull. So we're going to say, what if we only want to know the outputs of print 1 and print 2? So in that case, we can entirely drop print 3 from our task graph. So we specify that we want the outputs print 1 and print 2, and then we call cull on this dictionary with that outputs list passed in. So you can see this this simplified task graph with that entire side of print 3 removed. So that's a really helpful. That's like a really helpful operation, because it both reduces the size of the overall graph by removing part of it, which makes it easier to serialize and send around. And it also reduces the amount of work that Dask has to do when you call compute, because it doesn't have to do any of these steps at all. So in practice, cull is useful on operating partition data. So this is, we're going to be, in this example, it's the same time series. I'll write it to a directory using Parquet, and then we'll read it back in. And you'll see that there's 30 little tasks, one for each partition, each day of this data set. If you just grab one day, then and you let the optimization happen, then you'll see you just get one task instead of all these 30 tasks. And that's the cull happening, where Dask knows that you only need to read from this one partition to get that the data that you're interested in. And this has cascading effects, because now any future operations that you call on this slice of the data frame will only come from this one task. So it simplifies the task graph at this stage, and it also has cascading effects when you chain operations together. So inline, back to the fruits example. So inline is another example of what you can do of one of the default optimizations that Dask has. So you can, in this case, we can, there's these constants, val1 and val2, that just contain the string like apple or pear, and you can just replace those keys with the actual string. So because that's such a small value, it can be faster to just simplify the graph and embed those values directly in the graph. So this might actually be clear if we look at the actual output of the graph. So you'll see that orange, for instance, is embedded directly in the graph now, rather than this saying val1. So that's what inline does. Similarly, you can also inline functions, where instead of using a key to point to a function, we'll just embed the whole function directly. So the last step is fuse, which is combining several. So we've got this like purely linear graph at this point where there's two entirely separate columns. So we can actually fuse those tasks all into one. And that can make it, that makes the graph smaller, simpler, easier to serialize, like all the benefits that we've been talking about. So that's what that will look like, where all of the operations are fused together, and then the output is just there in this little square. So that's why if we scroll back actually to this this example where I said we're using call, it's actually using call and fuse, because the read parquet here is, it's actually read parquet and loc used together. So that's, the loc is, you know, this one. So those are actually being fused together into this one task in this optimized version of this graph. So that you'll see that a lot of times showing up in your graphs, that it'll be several names chained together. So if you want to combine them all, you can do call, inline, fuse. So a lot of times you'll see, if you look at the implementation of the optimizations on different collections, you'll see these kind of patterns where there'll be a bunch of different functions that are applied to the graph, and they each take the graph and a list of outputs, and then they will return a new version of the graph. So you can write your own custom optimizations. If you are working with an existing collection, you can just write your function that takes in some graph and some keys, and then returns a new graph. And you can then go ahead and set it using this. James talked about this a little. You can use config to set it either within a particular context or globally on the array collection, on the DataFrame collection. If you're declaring your own collections, you can also just set the Dask optimize method on them, and that will apply whatever methods you've defined in Dask optimize to the collection at the proper time. So this is a more involved exercise. It's based on the graph chain project, which you're welcome to take a look at. But it implements the graph chain project implements a custom optimization function that reads data from a cache if it's already been computed. So this example is actually from their README, where there's this task graph, and you'll notice that there's, for a couple of different keys in this task graph, the values of the task are the same. So it's the same function with the same inputs. So the goal of this exercise is to, instead of calling this function twice, once for this key and once for this key, to only call it once. So you can run this and you'll see that there's, it takes some time because it runs this create data frame twice. It runs the complicated computation twice. So since DFA and DFB have the same definition, you can write an optimization function that replaces one of the tasks with a key pointing to the other task. So it's kind of like the opposite of the inline thing, where we have this really expensive computation that we're computing twice, when actually we only need to compute it once. So this is the approach I'm suggesting is more simplistic than GraphGene uses, but basically I'm saying, can you replace one of the tasks with a key? So I'm going to give 5 minutes here to work on this exercise. It'll also count as a break, so do whichever you want. And I will put a timer for that. Okay, so I'm gonna start the timer and we'll meet back in 5 minutes. And if you have questions, let me know.
Just want to say there's been some great questions in the chat. Keep them coming if you have questions.
Okay. We will come back then. So there's some questions that came up in the chat. So there's a question about color coding the graph, the visualizations. So that people usually use color coding to look at the order in which the graph is going to be computed. So let me actually go back to something a little more interesting in the prior notebook just to show what that looks like. So if we go back to our first example, you can specify, let's see, color equals order, I think. And that will color it. Let's get rid of this to make this bigger. And I think I can set, there's some special arguments that I'm not remembering right now about pen width, but you can sort of see that this coloring now is representing, it goes from red to blue, and it represents the order in which this graph is going to be computed. Additionally, we now have these numbers here instead of the function names, which say the order. So 0 is like the first task that's going to be computed, and so on. So that's what I've seen people use colors for in the visualizations, but there's definitely a lot. There's some work that's ongoing about how to make these visualizations more informative and add more information into them. That's a good question. All right. So this is, just to wrap up this exercise, I have a couple different implementations. I couldn't decide which I liked better. But basically you want to look through the graph, find a value that matches, and then replace that value with the key. So this is one approach. Well, someone's drawing on the screen. And then there's another approach here, where you can list all the keys and then find the ones that replace the value with the one that matches. So hopefully this made sense and you understand better about how optimizations let Dask simplify the computation, improve parallelism, and you've learned about how these default optimizations work and how to apply your own optimizations, how to write and how to apply your own optimizations to your work. So with that, I'm going to pass it over to James to talk about schedulers.
Awesome. Thank you, Julia. Let me share my screen. Okay, so you should be able to see we're back in the overview notebook, hopefully. And yeah, so kind of reiterating what Julia just said, we've Act 2 of this tutorial, we talked about sort of advanced operations, aggregations, map blocks, things like that, blockwise, importantly, that we can perform on these Dask collections, and also task graph optimization. So like optimizing the output of these collections. So now in the third and final act, we will move on to the distributed scheduler specifically, which consumes this task graph and actually computes the graph in parallel. So let's move over to notebook 4 for the distributed scheduler. Yeah, so specifically what this notebook is going to cover is we're going to look a little more deeply into the different components that comprise the distributed scheduler, or rather the distributed cluster. We're going to talk about how you can inspect the cluster state and also how you can extend some of its functionality. So in this first section, we're just going to kind of give a overview of the distributed cluster, talk about the components that make up a distributed cluster, and talk about different methods you can use to actually deploy and launch clusters. So the components of a cluster are sort of these are made up of these three little squares here in this diagram. So there is a single centralized scheduler process, which is shown here in blue. And this basically accepts all the tasks that you would like to run It maintains a ton of states, so it tracks the dependencies between the tasks. Like I have to run this task before I can run this other task in the graph. I also have to like know where the tasks are running, so it will try and assign tasks to different workers, which are another part of the distributed cluster. It will try and, like, if there's already a task on a worker that is a dependency for another task, it will submit the next task to that worker, for instance. It'll try and be intelligent about that. And as I just sort of alluded to, the scheduler also keeps track of the state of various of all the workers attached in the cluster and submits tasks to those workers. So that brings us to the other component of the distributed cluster, which are the workers themselves, which are sort of indicated here by these 3 rectangles down here. So this particular Dask cluster has 3 workers, but you can have thousands of workers if you'd like. And this is where the actual computations happen. So the scheduler takes tasks from the user and submits them to be run on the workers. The workers are constantly communicating with the scheduler to update the scheduler with, like, what they're currently working on, like what tasks are currently being run, what tasks are complete and finished and they have stored in their memory and are, like, ready to serve that to the user whenever they request the result of the task. The workers, it's not indicated in this diagram here, but the workers, like, there should be little black arrows between the workers. The workers also communicate with one another. The scheduler can, say if there's 2 workers, worker A and worker B, and worker A needs something from worker B, the scheduler can tell worker A to go get that dependency for a task that wants to compute from worker B, and then the 2 workers will communicate with one another. And the last piece of the distributed cluster is the client process. And this may be the most familiar to folks in the tutorial. That's because this is the user-facing entry point for accessing the cluster. So the client will connect to the scheduler, and that's, you actually use the client to submit tasks to the cluster to be run. You can actually have, in this diagram, there's only one client, but Dask actually supports having multiple clients. So you can have multiple clients that you might have, like, different users using the same cluster. Each user might be in their own Jupyter Lab session, and they create their own clients that connect to the same scheduler. They can all submit tasks to that scheduler, which gets submitted to workers in the cluster. So those are sort of the main parts of the distributed scheduler. I do want to kind of outline a couple additional points specifically about the worker process, or the workers here. Those 2 points are that each of these workers, it's not really indicated in this diagram, but each of these workers actually has their own separate concurrent futures thread pool executor. That's not indicated here, but that's where the workers actually submit their tasks to run. The tasks that they're given from the scheduler, they will then run them in parallel on a thread pool executor. So each of these workers is its own separate process that actually creates its own separate, each process has its own separate thread pool. That can be, you can specify the size of that thread pool if you'd like, but by default, Dask will, like, inspect the machine that the worker is running on, see how many cores it has, and use that to inform how the size of this thread pool. And the other thing that's not indicated in this diagram that I wanted to point out is there actually is, like, another object in distributed clusters, which folks don't often talk about, and that object is the nanny. So this is actually Dask's default behavior. So by default, Dask will actually have a separate process that launches worker processes. So in addition to the client, the scheduler, and the workers, there would be these nanny processes which actually spawn the worker processes themselves. And the nannies are sort of a sidecar process that's constantly monitoring the worker process for, like, instance, the memory load or the memory consumption of that process. This is useful in particular, like, if you want to use client.restart, having some external process, in this case, the nanny process monitoring a worker, allows us to restart the worker if you want to explicitly by using client.restart. Dask also lets you set memory limits. So, like, if the workers start consuming too much memory, the nanny will automatically restart the workers for you. And that extra external process, in this case, the nanny, is needed and required to have that functionality. So I just wanted to point out those additional notes about the workers. So that is sort of the overview of the distributed cluster. Let's talk a little bit about deploying these clusters. So when someone talks about deploying a Dask cluster, really all they're saying is I'm going to, on some machines somewhere, I'm going to launch a scheduler process and a bunch of worker processes that are all connected to one another. That's like deploying, that's kind of all there is to deploying a Dask cluster. Don't get me wrong, there's lots of subtleties involved with that, but that is sort of the essential thing that one wants to do when deploying a Dask cluster. And there are a variety of ways to do that. I'm going to outline 3 different methods here. The one way that you can launch these scheduler and worker processes is to sort of a relatively low-level way, is when you install Dask and distributed, you'll actually get command line utilities. You'll get a Dask scheduler command line utility and a Dask worker command line utility. And those launch the corresponding processes. So for instance, whenever, like if you have some access to some large machine somewhere that you want to deploy a Dask cluster on, you can, like, let's say SSH into that machine and do Dask scheduler in the command line. That will launch a scheduler process and tell you the location for that scheduler process. So for instance, it'll say like, I'm a scheduler and I'm at this location. You can then like open up separate tmux sessions or like, SSH into the machine elsewhere, and you can launch worker processes. And keep in mind that the worker processes have to connect back to the scheduler so they can communicate with one another. So to launch a Dask worker, you use the Dask worker command line utility, but then you'll give it the address of the scheduler. So remember, the scheduler spits out its location here, and you'll just say, Dask worker, here's where your scheduler is that you should connect to. That will launch a Dask worker process and connect to the scheduler. You can do this a bunch of times. Like for instance, if you wanted 3 workers, you would just do Dask worker 3 different times. What's not mentioned here is there's also like an in process or in proc, maybe, I might be getting the name wrong, flag for the Dask worker command, where you can say like in proc equals 3, and that'll launch 3 workers automatically, which is just a single Dask worker invocation. So this is kind of a low-level way to, but commonly used way to deploy Dask clusters by using these command line utilities. Another way that you can launch a Dask cluster, so launching these scheduler and worker processes, is directly using Dask's Python API. So from dask.distributed, you can import the scheduler class, the worker class, and the client class, and you can just instantiate these objects. That's really all these, like, don't get me wrong, these command line utilities do other things too, but that is sort of the essence of what these command line utilities do, is they are spawning, or they are creating these scheduler and worker class instances. So here we can launch a scheduler. In Python, you would use this async with context manager to create a scheduler process. So that launches a scheduler. And then you can launch a worker. So up here, you launch a worker with the Dask worker utility and tell it the scheduler address. You have to do a similar thing here in Python. The scheduler class instance here has an address attribute. So you can do async with worker, tell it the scheduler to connect to, and that will create a worker process which connects to that scheduler. And then you can do a similar thing with the client. You can create a client and connect it to the scheduler. And then you can do things like, you can use the current features interface. You can say client.submit this function. I want to sum up range, so 0 up to, but not including 100, and then print out the result. So I'll execute this cell real quick, and you'll see like a bunch of output. These are just logs from my scheduler and worker and client processes. So you can see at the end, the result of this computation is printed out here. It's 4,950. We can see our scheduler getting spun up. We can see, like, here's that scheduler at, and then gives you the location part. We can see our worker getting spun up, and then some communication happening between them. We can see a clients connecting, things like that. I do want to maybe preface this. There's a reason there's little like warning signs here. In general, this is not recommended to deploy Dask clusters this way. This is crucial for certain types of workflows, but this is not generally recommended. This tends to be a little too low level for most Dask users. They actually don't need to go down to this level. In particular, you're seeing we're using things like async with and awaits, and there are just added complexities involved with using the Python API directly. So important for some use cases, but generally not recommended.
James, there's
Julia.
a couple questions that are coming up in chat.
Sure.
So there's one question that if you have multiple clients that are connecting, so in different Jupyter notebooks that are connecting to the same cluster, how does the total memory get shared among the workers?
Yeah, so how does the total memory get shared amongst the workers? Yeah, so the worker, basically each person connecting to the cluster, like it is sharing the memory, all the computing resources, including the memory resources on the workers. So you set a given, when you're spinning up your cluster, you set up a given memory for the workers themselves. Say, hey, I want each of my workers to have a memory limit of 30 gigabytes. And that now has to be shared amongst whoever submits all the tasks to the cluster. So yeah, there's no like partitioning of the memory in that way. Oftentimes, if people do need this sharing, they'll actually just launch different clusters. Launching Dask clusters is relatively lightweight. So instead of having people share one cluster, they'll actually have a separate cluster for each user. Hopefully that answers the question.
It's kind of like first come, first serve, right? In terms of who submitted a graph to the cluster. And then the other question is, what's the advantage of async in the workflow that you're talking, I guess in this one that you just went through?
Yeah, so the scheduler and worker processes are like Tornado asynchronous servers that are running. So sort of the asyncness of those classes is built in to sort of baked into the scheduler objects and the worker objects themselves. Yeah, so they need to process a bunch of messages concurrently. So that's where the async part is coming in.
Cool. All right, that's it. Yeah, carry on.
Yeah, no, great. Thanks. Please interrupt and ask questions in the future. That's like very, very appreciated. Okay, so there is this, great questions also from folks. So yeah, there are these two ways, the command line utility for launching clusters, which is relatively common. The Python API, which is good to know about and sort of fits some people's brains a little better, but is generally not recommended for the reasons we stated before. Actually, the most common way that we see people launch Dask clusters today is using what are called cluster managers. So Dask has the notion of like a cluster object. We actually have a cluster base class, which has a common API for doing lots of things you would want to, like common tasks you would want to do on your cluster. And we have different cluster manager classes for launching clusters on different hardware. So for instance, one cluster manager is actually baked into Dask itself, and it's called local cluster. So from dask.distributed, we can import local cluster. And what this will do is spin up scheduler and worker processes just locally on your laptop. So remember, the distributed scheduler does work well on single machines in addition to distributed environments. So here, what I'm going to do is instantiate this local cluster object. I'm going to tell how many workers I want. I should also say this part is optional. If you don't give it any parameters, it will like just inspect the number of CPUs you have locally and pick workers and threads appropriately. But you can tell it how many workers you would like explicitly if you have a desire there. So here I'm going to say, give me 4 worker processes. And then I want the thread pool for each of those workers. I want that each worker to have 2 threads. So I do that, and it will launch a cluster for me, and it will return back this local cluster object. You can see here are my 4 workers. Each of them has 2 threads, and you can specify the memory limit. I didn't do that, so it looked to see how much memory I have on my laptop and sort of set the memory for the cluster accordingly. And here we can see a link to the dashboard for this cluster. So this launched a scheduler and 4 worker processes for me under the hood. I didn't have to do anything. And the cluster object API actually supports a few common operations. So for instance, we can scale up and scale down our cluster. So I started off with 4 workers, and you can see I have 4 workers here. I can then say, hey, actually, I want 10 workers now. I want a little beefier cluster. So I can scale up my worker, or scale my cluster. And you saw really quickly, it said you had 4 and up 10, and then it went up to 10. You now have 10 worker processes. So it just launched 6 additional ones. I do some work theoretically, and now I want to scale back down my cluster. I can now scale down to 2 workers. You can see it scaled down to 2. So I can scale up and down, increase, decrease the number of workers in my cluster. I can also do things like retrieve logs from my cluster. So there's a get logs method, and you'll see, so this has like a nice HTML details thing here. You can see I can click on the scheduler to sort of expand that box. And here are all the logs from my scheduler. I can see when my scheduler started, when some workers attached, when some workers were removed, when I scaled down. I can also look at my cluster has 2 workers right now, and here are the logs for each of those workers. I can see here's where my worker started. It has the address for the scheduler it's listening to, etc. So you can get logs, you can scale up and down your cluster. You can also, importantly, shut down your cluster. This is important in particular when like you're running on something you're paying for, right? Like I'm just running on my laptop here. This isn't a big deal. If these were workers and schedulers were running on some AWS nodes, I want to be able to know how to shut them down so I don't have to keep paying for them. Yeah, so this is the cluster API generally. Here we are using specifically the local cluster. There are lots of other cluster objects in the Dask ecosystem, which I'm sort of linking to the documentation here for a few of those projects. And you would use one of these different cluster managers depending on the hardware you have access to. So for instance, if you have access to a Kubernetes cluster somewhere and want to launch a Dask cluster on that, you can use the Dask Kubernetes project. If you have an AWS account or a GCP account or an Azure account or other cloud provider accounts, a Hetzner account, for instance, you can use Dask Cloud Provider. That will launch Dask clusters on various cloud platforms. If you have access to a Yarn cluster, there's Dask Yarn. If you use MPI, there's Dask MPI. If you have access to some HPC job queuing system, like HT Condor or Slurm or PBS, you can use Dask Job Queue. And all of these projects, all these projects provide cluster objects, which will launch Dask clusters on the corresponding hardware. And the setup kind of looks similar. Like, for instance, if you use Dask Kubernetes, you'll import the kube cluster object from Dask Kubernetes and instantiate it. The ... here is like, there are Kubernetes specific keyword arguments that go here, but still spinning up the cluster is instantiating this kube cluster object. Same for Dask Cloud Provider. Spinning up a cluster on AWS looks like this if you wanted to use Fargate. And if you're spinning up a PBS cluster on a job queuing system with Dask Job Queue, you would instantiate a cluster like this. All the code after that looks exactly the same. You would connect your client to it and do your Dask stuff just like normal. Deploying Dask clusters here just means instantiating different cluster classes.
There's a question that came up in the chat that I think is actually a really good point, which is that like the API for all these different cluster objects also looks similar. So you can like do .scale, .close, .get logs on all of these.
Exactly. That's a great point, Julia. Yeah, so like scale here, like for the local cluster, just spins up new processes locally on my laptop. For Dask Cloud Provider, for instance, when you call the same scale method, it will automatically know how to launch new workers on new ECS or Fargate tasks, things like that. So yeah, the appeal here is the user interface is actually uniform across all these different backend hardware platform things.
There's a couple other questions that are coming up. So there's a question like, would you recommend spinning up a cluster on the total memory of the server or the free memory? This person saying that their worker's getting killed.
Yes, I mean, it depends. It depends largely on like what other things are going on that machine. So yeah, it depends. Like if you want to use the total memory of the machine, like that's totally fine. But then other processes can't necessarily be running on the machine. So it depends on how shared the resources are. Yeah.
Yeah, and then there's a question where in the cloud provider case, .close, this person saying seems to have delete semantics. So are there like, should it be that close only means off, or should it delete? I think that depends on the implementation in the different libraries that you've linked to here. Is that right?
Yeah, yep, it does. And so like, for instance, I think Dask Cloud Provider will try and clean up all the corresponding resources that it has generated as well. So when you call close, it'll not only actually shut down the worker process, but it'll also tear down all of the cloud resources that it's spun up in order to create that Dask worker as well. Yeah. And like on local cluster, it should shut down the process that started up. Like that is the cleanup for the local cluster, is just closing that, stopping that process.
Right. So it's a pretty aggressive method, I guess.
Yeah.
Okay. And then there's a question, how are the required schedule resources related to the overall cluster usage? So number of workers, complexity of the workload. I don't think I fully understand this one. But maybe you do.
Okay, maybe we can circle back to it then.
Yeah, let's do that.
Okay, great. Yeah, great questions, everyone. Keep going.
Yeah, if you could add more detail, that'd be helpful. Or you can ask with your voice at the end if that's easier. Okay, yeah. Back to you, James.
Cool. Yeah. thanks Julia for surfacing those questions, and thanks everyone for asking them. So yeah, here I've highlighted all these projects so far. These are all community maintained, like in the Dask GitHub org projects. I do briefly want to say that there are companies out there. So like disclaimer, these are companies Julia and I work for, and I'll just say like one sentence about them and we'll be done. There are companies like Coiled and Saturn Cloud that do offer Dask as a deployment, like a Dask deployment as a service offerings. So that's all I wanted to say, is that there are companies out there also that will help with your Dask deployment needs, or you can equally well, you could also use any of these open source projects here that also may equally suit your needs. So with that, putting back the completely community maintained open source hat on, that's it for deploying clusters. So the most common thing we see people, the most common way we see people deploying clusters is with these cluster manager objects. And we'll be sticking with the local cluster for the rest of this notebook. That's just because it's the easiest thing to spin up. You know, we all have local machines. We may not all have access to Kubernetes clusters. So speaking of clusters, let's spin up some clusters and inspect their state. So in this section, we're going to familiarize ourselves with the actual Dask scheduler and worker processes. We're going to sort of explore and get a sense for what kind of state is tracked in these processes. And we're going to learn how to inspect that state, even if they are on remote clusters. So before that, I have like a slight disclaimer. We're getting ready to dive into some stuff. That being said, Dask has great diagnostic tools that are already available without us needing to dive into things. In particular, there's the diagnostic dashboard and performance reports. So I will, real quick, I'm going to spin up a local cluster here and connect a client to it. And we'll sort of look at those diagnostics for just a second and look at performance reports. One thing I want to note here is I am passing in this worker class equals worker argument here. This is not required, generally speaking, and generally I recommend not to do this. What this does is it avoids creating that nanny process we talked about earlier on. The reason I'm doing this is so that we can actually look at the worker classes themselves later on in the notebook instead of looking at the nanny processes. So I just wanted to put that out there. That's why we're adding this here. And this is sort of just for kind of illustrative purposes. So let's go ahead and create a cluster and connect to it. So here we have our dashboard. And I wanted to just point out that once I like snap things in place here. Great. So I just wanted to point out that like Dask has these great diagnostic tools, and oftentimes these are totally sufficient. So like I will do some computation here, some like array thing, and I'll see all the tasks flying by. I'll see dependencies being transferred that happen quicker than I was expecting it to. So like maybe, you know, we'll make this a little bit bigger. Okay, great. So now like I do things and stuff starts happening, right? So tasks are flying by. I can see the memory that's being stored. Oh, that's why I made that small. I'm hitting them. I'm hitting the memory limit. Fun. Okay. Well, let's go back to making that the size it was before. So yeah, I've exceeded the memory limit of my laptop really quickly. So here we go. Things fly by. And we have state that we can see. And often this is totally sufficient. I do want to point out one like maybe lesser known diagnostic tool that you have available, and that's Dask's performance reports. So oftentimes people will know about it and look at the dashboard over here. Like we can see the overall status page where we see tasks and happening and the memory that's stored on our workers. Then we can like look at the system page to get like a sense for what's the CPU and memory load on my scheduler, for instance. What about my workers? What's the CPU and memory load on them? Oftentimes it's useful to like save this output to some static file. So that's what performance reports do. So you can import performance report from Dask.distributed, and just any computation you then do, you can use performance report as a context manager, and anything that happens inside that context of that context manager, all the corresponding, or not all, but many of the corresponding dashboard plots will then be saved to some file. It has a default name. You can also give it a custom file name. I'm calling it my report.html. So you can go over here and look at it saved this file, my report.html. And what you get over here is a performance report. So you can see it gives you information about your computation. This particular one took 2.6 seconds. Tells me how many tasks were in that computation, some information about my cluster, how many workers, how many threads, the memory, what version of Dask and distributor I'm running. It even actually saves the code that was used to generate this performance report. So like it has the actual code from, in this case, the notebook cell I was running over there. And then up here on the top, we have different tabs for different dashboard plots. So we can see the task sharing plot over here, the worker profile plot, the scheduler profile plot, etc. There are other plots as well. But this is super useful for like sharing this your workload performance with colleagues, for instance. Or if you're like doing profiling, like if you're tweaking a lot of things, maybe I'll start playing with this chunk size here to see what impact that has on my computations. It's useful to have some saved artifact that you can go back and compare against. Chunk size of 1,000 looks like this. Chunk size of 2,000 looks like this, and kind of not have to remember back to what the dashboard looked like. You actually have the dashboard saved in a static plot, which is really convenient. So anyways, that was like a long-winded way of saying that Dask already has lots of diagnostic tools, and oftentimes those are totally sufficient for many needs. However, we can dive in a little deeper and start to inspect the actual state of the cluster in a more programmatic way. So let's do that here. We'll start by defining this double function. And what it does is it will take in some input, and we'll skip over this for now. It will return twice that input. I've added some code in the middle of this function to like simulate some random failure. So like it will generate a random number between 1 and 0. If it's less than 0.1, it'll just randomly fail. This is a little contrived, but just to simulate some kind of failure happening in a computation. We'll then take this double function and submit it. We'll run it 50 different times, and we'll see what happens. So in the Jupyter notebook, we see that I'm getting some warnings saying some compute failed. In this case, like whenever I ran double with 31 as the input, it failed. When I ran it as 32, 43, 49, those all failed. They raised this value error. And in the dashboard, you can actually see that over here. All the green little tasks here, these are the double functions that ran successfully. And the black ones here, these are the ones where things did not run successfully. These 4 black rectangles over here correspond to the 4 times when I had this error raised. So that was to just kind of like put some state into the cluster. We've run some tasks now, and let's start to inspect the cluster. So the first thing we can look at is the scheduler. So not all cluster managers will actually have direct access to the scheduler. In fact, most of them won't. And by direct access, I mean like a reference to the scheduler class instance. The local cluster has that because it's some local thing that's running on my laptop. In general, like if I was running my Dask cluster on a Kubernetes cluster somewhere, or in AWS or on GCP, it's actually running on a totally separate machine, and I won't have access to that Python object. There are still ways to inspect that cluster state that are very similar to what we're going to show here with a local cluster, and we'll talk about that in a little bit. I just wanted to kind of highlight that one subtlety real quick. So since we're using a local cluster, we do have access to the scheduler object. So here we can look at cluster.scheduler, and here it is. Here's my scheduler. It's at a certain address, has a certain number of workers, and here are those 50 tasks that I just submitted, 4 of which failed. So we have access to the scheduler object. Let's start looking at it. Like I said before, it contains a lot of state. So for instance, the scheduler has an address. So here is the address for where my scheduler is running. It also like has a time started attribute. That is just calling time.time on the scheduler process whenever it starts running. It also keeps track of all of the worker states for all the workers. So scheduler.workers is some dictionary where the keys are the locations, the addresses for all the workers in your cluster. And the values of this dictionary are corresponding worker state classes. So I just wanted to note that these are not the workers themselves. They are separate worker state classes. So these are stored on the scheduler. They are not the workers themselves. They're sort of the scheduler's current understanding of all of the worker states, or rather the state of all the workers. And because the worker and scheduler, the workers and scheduler are constantly in communication, these worker states are constantly being updated. When the worker starts processing a new task, it'll let the scheduler know, and the scheduler will update the worker state object that it uses internally for that worker. So we can see here the worker state objects, have the number of tasks in memory, the number of the processing, etc. We can take this scheduler workers dictionary and like just pop off the first worker state object to look at that a little bit more. So here I just took the first value in the dictionary, and that gave us this worker state object for one of the workers. That worker state object also contains a ton of state. So like, for instance, it has an address, much like the scheduler has an address. We also keep track of all the workers' addresses. It has a status. So in this case, the worker is running. It could also be closed. Those are kind of the two worker states statuses. We can see the number of threads in the corresponding workers thread pool. We can also see a dictionary of all the tasks which are currently being processed on the worker. In this case, like the cluster is quiet right now. There are no tasks that are currently being processed, so it's an empty dictionary. But if tasks were flying around and being computed, this dictionary, the keys would be the corresponding keys for all the tasks, and the values would be the time that so far the task has been computing, like the current task duration. The worker also, like the actual worker processes themselves, also constantly have a heartbeat with the scheduler and will periodically send some information to the scheduler about its current state. We can see that state here in the worker state.metrics attribute. So we can see the worker will every however many milliseconds send a message that tells the scheduler how many tasks are currently executing, how many tasks are in memory, how many tasks are ready. That just means like, I have a task and I can compute it, but it's not currently being computed. There are other tasks being computed. It's kind of in the queue waiting, along with a bunch of other information. The current CPU load, the current memory load, the current time as signified by the workers, the current number of bytes that have been spilled to disk. If your memory starts filling up on your worker, the worker will start to spill things that it has in memory to disk. So yeah, etc. There's lots of other content here. Anyways, these messages constantly get sent to the scheduler, and the scheduler is updating these worker state objects. For instance, we can kind of see that by looking at the last seen attribute for the worker state. What this does is it keeps track of the last time that the scheduler got a message from a given worker. So for this particular worker, this was the last time it was seen. We can add a for loop here where we print out worker state last seen and just like sleep for a second and do this a few times. And we'll see that this last seen attribute keeps going up by about a second, actually. That's because this worker state class keeps constantly getting updated as the scheduler and worker communicate with one another. So that's the sort of the scheduler and how it keeps track of various worker states. In addition to keeping track of like information about the workers in the cluster, it also keeps track about all the tasks that are happening that have been submitted to the scheduler and certain metadata about those tasks. So much like there's scheduler.workers, which have all the worker states, there's scheduler.tasks, which has all the task states. So scheduler.tasks is a dictionary. The keys are all the corresponding keys for a given task that the scheduler knows about. And the value is a task state object. This is similar to the worker state object, but it's sort of about the task instead of about the worker. So we can do something similar. We can, like before, we kind of plucked out the first worker state object. We can do the same thing for the tasks to get a task state object, which we can see here. And this has some, like the HTML wrapper has some information about this task. It says, oh, this task is in memory. That means it was successfully computed on the worker. It's stored in a certain worker's memory. And actually, we have the size of the result. It's 24 bytes and the key for this particular task. Task states also contain lots of other information. So like task states have a key that is the key for a unique identifier for the task. It has a state. This particular task happens to be in memory. It has a who has attribute, which is a set of all the workers who have this task in memory. So right now, actually only one worker has this task in memory, but in theory and in many circumstances, there may be duplicates of the same key, the same task on multiple workers. We have the size of the result of this task. We have the type, in this case, it's just an integer. And like you can also tell tasks that they are allowed to retry a certain amount of times if you have like a task that is expected to be flaky, for instance. In this case, it's 0. So that was sort of a whirlwind tour of lots of the state that's on the scheduler. Let's now do an exercise. Let's spend the next 5 minutes going through and kind of continuing to get familiar with all the state that is tracked on the scheduler and try and answer these 2 questions. The first question is, how many keys, or sorry, what are the keys for the tasks which failed? So we had these 4 tasks here which failed. Can you figure out what the keys are for those tasks based on all the state tracked on the scheduler? The second question is, how many tasks successfully ran on each worker? So we had tasks that got distributed to a bunch of different workers. How many tasks were successfully run on each worker? So let's spend, the next 5 minutes working on this, or you can take a break. Julia, do you have the handy timer ready? I'll try and pull it up. Oh no, we have to watch an ad. Thanks, Julia, for pulling it up.
Yeah, and I'm collecting a bunch of questions from the chat that are like kind of bigger topics that we can talk about at the end, just in case I'm not addressing your question directly. That's what's going on.
All right, looks like we are at 5 minutes. So let me share my screen again. Yeah, thanks again for sharing the timer, Julia. Okay, should be seeing Jupyter Lab again. What are the keys for the task which failed? So here is the solution. One possible solution is to loop over scheduler.tasks. Remember, that's a dictionary with key values, which are like key names and task states. What we can do is like get a list of all the keys if the corresponding task state is errored. So here we can see these are actually the 4 keys which correspond to the 4 times that this task happened to fail. This is just one way to go about it. There are, I'm sure, other possible solutions as well. The next question, how many tasks successfully ran on each worker? Here I actually included just two solutions that came to mind. One is sort of the brute force way, which is to do something similar initially. So up here, we got the error task by looping over scheduler.tasks. Here we do the same thing. So this line is exactly the same, just to get these are the keys which failed. Then we can create a default dictionary of type int, and then loop over our scheduler tasks. So we can look for, basically loop over all the tasks the scheduler knows about and see if the key is in this list of failed tasks. So like if this task failed, then just continue. It did not successfully complete. Otherwise, if it did successfully complete, look at all the workers who have this key and like add counter +1, just increment counter. And that way we get a dictionary that looks, or like a default dictionary, which looks like this. So we can see we have worker addresses for the keys and the total sum for all the workers with successfully completed tasks for the values. Another way to do this is to look at like the worker state metrics. If you recall, scrolling up a little bit, the worker states contain the number of tasks that are currently stored in memory on each of the workers. So in this case, we could just actually pluck that information off the worker state to get the number of tasks, which can, maybe I'll add a couple new lines here so we can see the difference between these two solutions. So yeah, this would be another possible way to get how many tasks successfully completed on the workers. Okay. Maybe let's do, I just want to highlight one extra section here and then we'll circle back to questions because I saw there are a bunch in the chat. So far we've been talking about the scheduler and inspecting its state. So the local cluster, in addition to having access to the scheduler object itself, actually has access to all the worker objects as well. Those are stored on cluster.workers. I just want to note really quick, this is why we added at the beginning when we created this cluster, that worker class equals worker, to avoid that nanny process altogether so that this dictionary actually contains the worker processes. If we didn't include that worker class equals workers, this would contain the nanny processes themselves, which just don't have the rich information the workers do. So that was why we added that at the beginning. We can, again, pluck off the first worker object in our cluster to get this worker here. And we can look at lots of the state on the worker. I'm not going to like kind of drag this out. This is kind of similar to the scheduler. We can just look at all the various state. Workers have addresses. They keep track of the number of tasks that are currently being executed on the workers. In this case, it's 0 because we don't have any tasks that are currently being computed. It also keeps track of a running number of tasks that have been computed on the worker throughout the entirety of the worker's lifetime. So in this case, this worker happens to have already computed 69 tasks throughout its lifetime. We can see the number of threads on this worker. And actually, since we're looking at the worker itself, we can actually look at the thread pool object here, where the thread pool executor, where it actually submits tasks. So this is the thread pool executor in the worker where tasks are actually run. We can look at the keys that are currently stored in memory on all the different workers. And we can actually get the values for all those keys too. Workers have a .data attribute, and this is where they store all the results for all the tasks they've computed. So it's some complicated buffer RLU thing. That's because this supports spilling to disk. But the take-home message here is this data attribute is still just has a dictionary interface. It has a mutable mapping interface. So we can just basically call get item on it to get like you give it a key like a dictionary, and it'll return the value will be the corresponding value for that key. So we can loop through all the keys that are stored in memory on this worker. Those are the values, and then the keys and the corresponding values. We can reach into our worker data mapping to get the actual value for things that are stored in memory. So yeah, that's all I wanted to really say about the worker. You can go through similar exercises and start asking questions about the additional state that's stored on the worker. So I'll kind of leave that as an exercise for you to go through later. The last thing I wanted to talk about, actually, before doing a round of questions, is so far we've been inspecting the state of a cluster, which is a local cluster. And that's great because we have access to the scheduler and worker objects, and we can kind of, futz around with them. But as I said earlier, that's not always the case. And in fact, that's usually not the case. Usually the scheduler and worker processes are running somewhere else on some other machine somewhere that you don't actually have access to those Python objects. We can still inspect those schedulers and workers in those scenarios, though, using the client.run and client.run on scheduler methods. So here I'm linking to the corresponding documentation for these two methods. Keep in mind, you'll always have a client for a cluster because that's like the user-facing entry point. That's how you connect to a cluster. So you'll always have access to a client. So what client.run does is allows you to run any function on your worker processes, and then it'll return the results of that function. So for instance, I can say, I can import OS and run client.run. I can run os.getPID to get the process ID for each of my workers. So I'll run that here and return the result. What that did is took the OS getPID function, shipped it off to all the workers, ran it, got the result, shipped it back, and put it in this nice dictionary. The keys here are the addresses for the various workers, and then the values are the process ID. Because I'm not using a nanny, these all happen to have the same process, or these all have the same process ID. In general, these would be different if we had nannies, because they would all be running in their own different, they would all be spawned by different processes. So this runs this given function on all your workers. You may only want to run a certain function on a subset of workers. So there's also a workers keyword argument that you can pass to client.run. So here I will just get the addresses for a couple of workers and then pass that to client.run. And that allows us to run the, in this case, the getPID function just on two of the workers I've specified. What's really interesting, and so that's useful in itself, like you can run things on workers. What's really useful is you can like use your own custom functions and run those on workers. And actually, if that function has a Dask _ workers parameter for that function, whenever that function gets run on the worker class instance itself will actually get filled in for that Dask worker parameter. So you'll have access directly to the Dask worker class, even though it's running on the remote worker. That's because we're like running the function on the remote worker itself, where we have access to that class. So here, Dask workers have names, for instance. So you can define a get worker name, which takes in Dask worker and returns Dask worker.name, remembering that this will be the actual worker instance. And there we go. This isn't super informative. Like by default, I didn't specify any names when I created these workers. So by default, it actually just gives it will assign it'll increment the name to be a number, an incremented number. So we have the address and corresponding name for the workers. If I had specified some custom name, you would see it here. Same thing goes for the scheduler. Instead of using run, we can use client.run on scheduler. And that allows us to run some function on the scheduler itself. We can also run custom functions. And if that custom function, this is optional, but if it has a Dask scheduler parameter, it will actually fill in the scheduler class instance itself into this function when it's run. So before, whenever we looped over all the scheduler's tasks and saw which ones were errored to get the list of keys, we can still do that with run on scheduler. We can write a function that will do that, get errored tasks. This looks exactly the same as what we did before. And we can run that and it returns it runs it on the scheduler and ships back the result. So here are those 4 keys which were failed. We're getting, and this would work This works on a local cluster, as we see, but this would also work on any other cluster you could have running, even if the workers and scheduler are remote. Cool. And let's go ahead and close down this cluster. And with that, maybe we can shift to a quick Q&A session. Julia, you said you were keeping track of some questions.
I have been keeping track of questions. I've been trying to group them a little bit to see if you can just like, I'll give you a starting point and you can just talk for a while. But people, like once we do a bit of that, maybe if people have more questions, it might make sense for them to ask them themselves. So, okay, so there's a lot of questions about memory. So, so how does Dask know what the memory of the task, like how much memory will be required for tasks in order to not overwhelm workers?
Yeah, that's a great question. So Dask, as we said earlier, like keeps track of the task state. Where is it? Anyways, the task state has an in bytes argument. And Dask will like over time actually learn it will have estimates for the size. Initially, it has bad estimates for the memory consumption for tasks because it hasn't actually run them and gotten outputs. But over time, it will use that in bytes information on the task states to have an estimate for when you run future tasks, what it thinks the memory consumption will be for that task.
And you can explicitly say what the memory expectation of a task is, right?
That's a good question. I'm not sure.
Okay.
I know you can for the duration of a task. Dask will also learn how long tasks take to run.
So the following question, like how do you stop workers from requesting more memory and getting killed?
Yeah, so you can set a memory limit, for instance. That's like the typical thing people do is they set a memory limit, and Dask will use that memory limit like to do various things to try and, when a worker starts taking up more memory, try and lessen that memory load. Eventually, if those things don't work, the worker will just get restarted. If the worker ends up taking up too much memory, that'll hopefully avoid any issues where the worker starts, just using more memory than you've said it's allowed to use. A couple of things that happen to try and avoid memory over memory consumption is one thing is spilling to disk. So like, if the worker has lots of tasks results in memory, it will start flushing those down to disk. That will reduce the memory burden on the worker. There's a performance hit because like now whenever you need those results, it will have to pull them from disk first. So there will be this extra loading computational cost, but it reduces the memory burden. Also, at a certain point, Dask workers will pause and not start running new tasks. Like once they have their memory, the memory they're consuming is a certain fraction of the memory limit you specified, they will keep working to the task they already have that they're already working on, but they will go into this pause state where they don't start running new tasks. And the idea is that eventually things will start to spill to disk there, or tasks will become intermediate results won't be needed anymore, and it kind of helps us reduce the memory load a little bit there too. So those are a couple things that we do to sort of help mitigate memory issues. And then the hard stop is restarting the worker. I do want to mention that there is a talk. I'm forgetting if I think it maybe is tomorrow. Guido Imperile is a coiled engineer and works on Dask, who's giving a talk on memory management Dask. This is like a current, there's a large effort right now to improve Dask memory management, and he'll be talking about that. So I also recommend folks, if you are available, to go check out that talk.
Okay, I think that makes sense. If there's a question like, so if you have a collection, a flat collection of expensive tasks, will Dask schedule them all at once?
A flat collection of expensive tasks. I guess I'm not sure what that.
I guess like a single layer task graph that are all memory intensive. I imagine since if Dask hasn't seen that type of task before, then it won't know what the memory expectations are necessarily, or might not have a great understanding.
Initially, yes. Yeah.
Okay.
Yep.
So I think yes.
Yes.
And then there's a question about is there a way to queue tasks being sent to a scheduler so that you can prevent certain tasks, so you can control that behavior and like sort of, I guess, give the scheduler access to the task graph over time rather than sending it all at once? Does that make sense?
Yeah, that's a good question. No, so like today, you submit tasks and they go immediately to the scheduler. You can't, that process is not throttled. Yeah.
Okay. I think those are most of the memory ones. So when building the task graph, does Dask optimize the graph also looking at the memory footprint of the tasks?
Dask keeps track of the memory load that's the workers are currently under. And like I said, workers will start to go into pause states, and like we won't be sending more tasks to workers for them to work on. So it does take this into account in some regards.
Okay. Okay, I think those are kind of capture a lot of the questions. There's one that just came up about what scenario, I guess this is just about intuition about Dask. So what scenario does the scheduler like better? A high number of single-threaded workers, so like one CPU and one thread per worker, or a low number of multi-threaded workers, so 12 CPUs, 4 threads per worker?
Yeah, that's a great question. Also, my headphones are beeping like they might give out soon. So if you can't hear me, let me know. If they die, I'll take them out.
I will.
Yeah, that depends. The scheduler has no preference there, I don't think. It's more so about communication costs, and it really depends on the actual computation you're running. So if you have more workers, like if you had 1,000 single-threaded workers, there's going to be lots of dependency transfers. Again, depending on the structure of your graph, there will more than likely be lots of dependency transfers there. There's also, so for instance, having multiple threads, like you could have tasks which are dependent on one another that are happening in different threads, or rather two tasks that are inputs to a future task that are happening on different threads in the same worker that now don't have to be transferred to another worker to run the next task. So there's serialization and communication costs associated with that. There's also like the same arguments for the single threaded workers, the single machine workers for threads versus processes, the multi-threading scheduler versus the multi-processing scheduler. A lot of those same arguments still apply to distributed schedulers, like for a single worker. So things like GIL contention, if you're doing like, if the code you're running releases the GIL, like if it's numeric Python code, like NumPy or something like that, then multi-threading is okay. But if you're doing things like Python string manipulations or anything that holds onto the GIL, then you might still have GIL contention within a single worker. So you might want to adjust the size of that thread pool accordingly there, depending on the actual tasks that are running. Hopefully that answers the question. It depends, I guess, is the short answer.
Yeah, I think that helps build intuition, even though ultimately it depends on what you're running.
Yeah, those are some of the things to think about.
Yeah. Another question that came up that's kind of related to the notebook that you were looking at. This person's asking, like, the warnings like distributed utils performance, garbage collection took whatever percent of the CPU. Are those warnings from the worker, coming from the worker, from the scheduler, from the cluster? Like what is that talking about?
Yeah, that's a good question. It's definitely happening on the workers. It might also be happening on the scheduler, but I'm not 100% sure off the top of my head. Basically, we are, Dask will monitor the garbage collection process. We actually put like a callback into the GC collection on, for sure, the workers. And like I said, I think also the scheduler, but maybe not the scheduler, and monitor that. So if garbage collection actually takes a long time, we have a callback in to raise a warning. And that could be for a variety of reasons. Why it's taking a long time is sort of a separate question than surfacing that it is taking a long time. For instance, you could have a lot of small objects on the worker and just taking a long time to clean those up. Or you could have some maybe very complicated object where garbage collection actually just takes a long time to clean up that object.
Yeah. So there's also a question about, like, if you've already computed the a task on a particular worker and another task depends on it, is that result recomputed?
Typically, it depends. Like if there's only one dependency for that task, typically the scheduler will actually assign that task to the worker that already has that task in memory. So it doesn't transfer it, it just stays in the worker. Like if there's task A and task B, which depends on task A, and task A is already on a worker, the scheduler will generally assign task B to that same worker because it already has the result stored in memory.
And if that result were released, if the results from that task were released before task B was able to compute, what would happen then?
Yeah, eventually it'll get recomputed. The scheduler keeps track of all of that stuff. So like if that worker goes down or something like that, then the scheduler will know all the keys that are on that worker, and eventually those will get recomputed on different workers.
All right, that sounds good. So this, so there's another question that's come in about Dask.compute scheduler equals thread. So that's not about distributed schedulers,
Yeah.
but they're saying it's not a real multi-threaded implementation because of GIL. So how can this parallelize computation?
Can you say the question again?
Yeah, I think you can also unmute Gail and ask the question yourself if that might be easier.
Yes, thank you. Do you hear me?
Yep.
Yes.
Okay. Yes. Yes, I'm a bit confused because I thought that phrase pool executor was not a real multi-threading because of the chill. Only one thread can be executed at a time. So how can this do? Oh, sorry for my English. How can this generate real parallelism when you do computation on numbers? Because there is no I/O, so there is no parallelism, in fact. Because thread pool executor is only switching from one thread to the other when there are I/O. And when you compute with scheduler equal threads, you've got real performance enhancement. So I don't understand this.
Okay, yeah, I think I understand the question. Thank you for asking. So yeah, like Dask just is a convenient way to use Python's existing parallelism for the single machine schedulers. So you're right, we do just use a concurrent features thread pool executor for the multi-threading scheduler on a single machine. And yeah, you can run into GIL contention issues there, where you actually won't be very effective in your parallelism. Oftentimes, like Dask users are running numerical code, which do release the GIL. So they'll be running things like NumPy or maybe Numba functions, which they're explicitly saying release the GIL, or some other C or Fortran library where the GIL is not held. So you don't run into those issues. So you actually can have multiple Python threads running non-Python code, to be clear, running non-Python code in parallel. If you're doing things where the tasks you're running do hold on to the GIL and you run into this GIL contention, then you should probably not use the multi-threaded scheduler. You should instead use the multi-processing scheduler. That has the benefit that each process has its own GIL. So like there's not GIL contention between the processes. That's like the added benefit you get. So you'll generally get better, more effective parallelism there. The downside is like they multi-processing, they don't have a shared memory space. So like multi-threading, like multiple threads do in Python. So you actually have to take your objects, the things that are being executed in each process in the executor, they actually do have to be serialized and sent between the different processes. So that introduces some overhead. So there's sort of a pros and cons associated with both these routes. So at the end of the day, it will depend on the actual tasks that you're running as to what's most effective, threads versus multi-threading versus multi-processing. But both those options are available for the single machine schedulers. Hopefully that answers your question.
Okay, there's a question about, are there any like rules of thumbs for how many resources the scheduler needs? So I said that I normally set my schedule to be the same size as my workers on like a Kubernetes cluster, but do you do something different, James? Do you have a sense of that?
Also, I took my headphones out because they just gave out. Can you
sound
hear me?
fine. Yeah.
Okay, cool. Just want to make sure. Great. Yeah, I tend to do the same. I tend to just use the same like resource allocation for the scheduler as for the workers. Although that's just like because it's easy, right? That's maybe not the best the best answer. And in general, I don't have a ton of recommendations about the scheduling resources in terms of like number of CPUs or I guess the number it's single threaded, so like it doesn't have to have a lot of CPU power. But in terms of memory, I guess in particular would be the thing. That'll vary depending on your workload. Like I often tend to see people using like, I hesitate a little bit to even say an answer, but like 10 gigabytes-ish seems fine for most workflows, even large workflows. But your mileage may vary there as well.
Yeah, and if you find yourself, if your scheduler tends to be dying because of memory errors, and you feel like it's not too small, then you might want to rethink how you are setting up your computation, because that tends, in my experience, it tends to mean that you're sending a lot of data through the scheduler, which is not always a great idea.
Yeah, I should say this also tends to, at least based on the issues that are opened up in Dask and distributed, this tends to not be a widespread issue. So hopefully the memory footprint on the scheduler, it's sort of designed to be relatively small, and hopefully it is in practice. I think it is, but let us know if it's not in your particular case.
Yeah, and then there's another question about how to access a worker's thread pool executor. So the example is if I have a task that uses multi-threading and want to use that, then in the scheduler would want to use multiple workers, but they want to put them all in one worker. They're wondering if they can just get access to the worker's executor directly. I think I understand that question. Jose, jump in and correct me if I said that wrong.
Yeah, what that question sounds like to me is I have like I have nested parallelism. Dask has its own parallelism that it takes care of. I have some tasks that I want to like control at a finer grain its parallelism. In general, we don't recommend that nested level of parallelism. I would either use just your level of parallelism or let Dask take care of the parallel part for you. So anyways, generally that's not recommended in mixing those two. To your point though, like maybe you have some tasks, a bunch of tasks you want to assign to a specific worker. That's also, I was kind of getting that from that question a little bit. You can also assign, you can arbitrarily assign any task to any worker and say, I want to run this task on this worker. Like for instance, client.submit takes a worker equal, or maybe workers equals, and you can give it the addresses for whatever workers you want to assign that task to. So if the question, like maybe there may be another way to accomplish what you want, still just using Dask for the parallelism part, saying assign all these 100 tasks to this worker.
Cool.
Yeah, hopefully that answers the question.
Yeah, okay. There's a long one. Matt, do you want to just unmute and ask this one directly?
Yeah, sure. I mean, my question basically is just about work stealing. And, you know, it seems like I run into a lot of cases, particularly when doing some like complicated shuffling operations where I'm, you know, doing a group by apply on a full data frame, where just you'll have, you know, a significant proportion of the workers that are assigned no tasks, and then like the rest of the workers are assigned a bunch of tasks. And I was wondering if work stealing is like applicable in this case, or if that's just an issue with like transferring partitions across workers.
Yeah, I don't have a good answer for you right now. In general, I think work stealing works quite well. Like it shouldn't be piling up. Work stealing, if I'm hearing you right, shouldn't be the cause of piling up a bunch of tasks on certain workers and not on other workers. Could be for some other reason though. It might be worth maybe like syncing up offline and diving in a little deeper into your particular scenario.
I would say if you're literally using group by.apply, you probably are doing more shuffling than you need to do, and you might look into doing custom aggregations instead, where then you don't do any reshuffling, you just group the partitions and work on those group by outputs directly.
Yeah, I appreciate that. In this particular case, it does actually need a shuffle, but that's definitely something I've been keeping in mind.
Yeah. Okay, a couple more came in. James, if you're still game for this.
Can I put this on pause and we can finish up, and maybe I'll go through the rest of the notebook quickly and then we'll circle back.
Oh, are you not done with the notebook?
Nope. Yep, still one more section. So yeah, no worries.
Sorry, I thought you were at the end of the notebook. Okay,
yeah,
go for it. Yeah.
No problem. These are all great questions, but let's circle back real quick.
Yeah.
Okay. The last thing I wanted to talk about was the Dask plugin system. So far, we've talked a lot about inspecting the scheduler and workers, their states, seeing what is stored on them, getting a sense for these are the tasks that have errored. Here's my thread pool executor on my worker, things like that. I want to talk about extending the functionality of the workers, because inspecting the state is super useful for, like, in particular, debugging things. But sometimes you want to actually change the functionality of schedulers and workers. So to do that, Dask actually has two different plugin systems, one for the scheduler and one for the workers. And what this allows you to do is define some custom logic that you want to run on either the scheduler or the workers when certain events happen throughout the life cycle of a scheduler or workers. So for instance, for the scheduler, like when a new worker spins up, you may want to have all the normal things that happen when a worker spins up, but then run some extra additional code that you, like custom code that you may have. Or on a worker, when a task transitions from processing to memory, does that state transition from the worker's currently executing this task to it's done and stored in memory, you might want to execute some other custom code. So Dask has a scheduler plugin and worker plugin class. And to create your own plugin, you can just create your own subclass of these classes and define certain methods, and we'll display what those methods are. So for the scheduler plugin, these are the methods that you can implement. And each method here corresponds to like some event happening throughout the scheduler's lifetime. So for instance, start is when the scheduler starts up. Transition is when a task transitions between any states. So like I said, processing to memory, for instance, processing to error is another useful one for debugging. When a worker is removed, when a worker is added, same thing for the clients. Like when a client attaches to the scheduler or is removed from the scheduler. And we also have similar methods for the worker plugin. When there are fewer methods, but when the worker spins up, when the worker spins down, when tasks transition, and whenever a task is released on the worker. So I linked to the documentation here. These are like the actual names of the methods you can implement. I link here to the scheduler and worker plugin systems. Documentation, and you can look here for the actual signatures for these methods themselves. So like the add worker for the scheduler plugin method should have this signature, where we have the scheduler and the worker, and then any particular keyword arguments that get piped in for adding workers. So yeah, let's look at a simple example and then maybe a more real world example. So what we can do we can define our own custom scheduler plugin. In this case, it's a counter scheduler plugin, which will, when we create this object, it'll assign an in-tasks attribute and assign it to 0. And what we're going to do is just keep a running tally of all the tasks which have successfully been, or the number of tasks which have been successfully run and completed on the scheduler. So for instance, to do that, we would define a custom transition method. We want to hook in to when tasks transition from one state to another. And this is what the signature looks like for that when you go to the documentation. This is the signature it should have. What gets piped into this method is the actual key for the task that's being transitioned, as well as the starting and finishing states for the task. So if it's going from processing to memory, processing to error, ready to processing, something like that. And then also there are some additional positional keyword arguments that depend on the actual transition that's happening as well. So what we can do is if we want to look for tasks that have successfully completed, we can look for tasks which are transitioning between the processing state. So they started out in the processing state and they're transitioning to memory. So that means they are stored in some worker's memory somewhere. And whenever that happens, we will just increment in tasks by 1. And that will keep track of all the tasks which have successfully completed. To add this plugin to a particular cluster, we can, in this case, create a local cluster and connect a client to it, and then use the scheduler's add plugin method here to add this plugin class. So what that did is that created a new cluster, and that added the scheduler plugin to it. I'll refresh my dashboard over here so that we get this new cluster happening, or being displayed over there. So I can look initially, my counter is actually at 0. I've processed 0 tasks successfully. And then I will submit some work. I'm going to submit some function. I'm going to actually submit 27 different tasks, and we'll wait for them. We can see over here, here's all of them being processed. And now my end tasks is 27. I've successfully run 27 tasks. If I was using that double function from earlier and like there were random failures, this wouldn't be 27. This would be however many actually successfully ran. I'll go ahead and close down this cluster. So that's like a simple example of one way we can extend and track some own custom state that we want to in the scheduler. Another more real-world example is the pip install worker plugin, which is actually included directly into distributed. So here I will actually print out the source code for the pip install worker plugin. So you can see that we are creating, that this is a subclass of our, we take our worker plugin base class and create a new subclass. And the user can pass in a list of packages and some pip options. So like if you want to pip upgrade or whatever the case may be, pip install upgrade, that is. And those are all kept on the instance. And then we override the setup method for the worker. So this happens when the worker is starting up. This method will get called. And what this does is it on the worker will open up a subprocess which calls pip install with whatever pip packages and pip options you've specified. So this will ensure that certain packages are installed on your workers. This is like not the general way to manage software environments in a Dask cluster, but this is often really useful if someone has a Dask cluster up and running and they're like, oh crap, I forgot to install whatever package I need. There's like this one package I forgot to include in my Docker image. Instead of tearing down that cluster and spinning it up, they might use the pip install plugin to just make sure that package is installed automatically on all the workers for this cluster. So this is like a nice convenient way to sort of patch the environment. So this is maybe a more real world example of a plugin that people might use in the wild. And so the scheduler has an add plugin method you can use to add scheduler plugins. To add a worker plugin, you can use the client.registerWorker plugin method to send that plugin to all the workers and make sure it's stored on the workers. The last exercise, which maybe I'll just leave and we can do questions for the last few minutes. This is to create a task timer plugin. So create a scheduler plugin. Here's sort of a scaffolding for what it should look like. And basically fill out this ... here. What we want to do is keep track of how long each task takes to run. I'll sort of leave this as an exercise. You can hit this ... here if you want to expand a solution. So yeah. Also, I'll just maybe put a bow on this and then we can do questions. Thanks everyone for the time. I really appreciate it. Julie and I both appreciate all the time and attention people have let us have. And yeah, here's some additional resources: the Dask and distributed source code, Dask and distributed documentation, the discussion board on GitHub. If you have any usage related questions, if you run into a bug or have a feature request, there's the Dask GitHub issue tracker. And if you'd like to get involved, that would be much appreciated and very welcome. You can check out our contributing guides here, which I linked to if you would like to get involved contributing to Dask. So yeah, with that, thank you. And maybe we'll spend the next couple of minutes going through the backlog of questions. Does that sound okay, Julia?
Yeah, and sorry for chopping your section in half like that with all the questions.
No worries.
Yeah, there's a couple more that have come in. So one is like another intuition question. Is there a ceiling for the number of workers or maybe total threads that a single Dask cluster can manage?
Yeah, in theory, no. There is some overhead associated with like there will be some overhead, communication overhead as you increase your worker size. So we've seen like thousands and tens of thousands of workers run successfully, like clusters of that size. run successfully. I don't know that we've seen 1 million workers, for instance, running on a Dask cluster. I'll also plug, there is on the last day of this summit, there is a conference, there is a workshop on scheduler performance, which I recommend going to. We'll talk a little bit more about this, improving the scheduler's performance and improving the overhead associated with, for instance, among other things, adding more workers. But yeah, short answer, thousands, tens of thousands, millions, I don't know.
Yeah, that makes sense. I think, so I answered this one, but just to check to see if you agree. So when would creating a scheduler plugin be a good way to connect to external logging tools for managing cluster state? Or is there a more built-in way?
Yeah, no, that seems good. Dask has a couple of other logging systems, like it uses Python's normal logging system. You can redirect that. Like if you're using AWS CloudWatch or whatever, you can redirect the scheduler logs to CloudWatch if you'd like. You could also do this through some other mechanism of your choosing with the scheduler plugin. That's another totally valid way to do that.
Great. And can the plugin catch task errors?
Can the plugin catch task errors?
Yeah.
Not like in the try except way of catching errors in that way, but like you can hook into the transition between processing to error transition. You can hook into that and get information about like, oh, this task failed. You can look at the task state, and I think that actually will have the exception stored in it. So you have access to it. But yeah, it's not, you can't do like a try except in a plugin in the same way.
Cool. Looks like we're at time, so I just want to make everyone aware of that in case you're trying to go. Okay, great. Nathan's saying that as well. So if you have more questions, feel free to ask on Slack. There's a channel specifically for this tutorial. And yes, with that, it's over.
It's over. Awesome. Thanks everyone for attending. Really appreciate it. Yeah, we'll be on Slack. Let us know if you have any questions.
Yeah, the channel is called the name of this tutorial, Hacking Dask or something.
Hey, so everyone, let's thank James and Julia for a most excellent presentation on hacking Dask, diving into the internals. And let's take it off to any further conversation to Slack. Thank you so much.
Thanks, everyone.